training seminar thing that y'all did today help make it, again, reinforcing what I think we've all been saying, or I've been saying throughout the semester. The ACT is less of a test of what you know and more of how well you can take a test, which is kind of nice. But what we're doing today is we're going to go through part way through this here. We'll finish it tomorrow. And then with the rest of the time, I'm going to go back over what we did yesterday for those that missed, that were not here. Now, the first thing we're going to be talking about with these logarithms, bless you, is this here. Log base b of y equals x if and only if b to the x is equal to y. Log base b of y equals x. This is true if and only if b to the x is equal to y. We can switch from one form to the other. And the reason we want to do this, or this is helpful, is sometimes having it in exponential form is going to be more helpful or more useful than logarithmic. And sometimes having it in logarithmic form is going to be more helpful or useful than exponential. So when we look at this here, we have log base 2 of 16 equals 4. And we want to rewrite it as an exponential. Now log base b of y equals x if and only if b to the x is equal to y. So we're going from logarithmic log form to this exponential form. Now as we look at the original equation, log base 2 of 16 equals 4, what is taking the place of b? Almost. So 2, because that number that's written lower is the base, which is our b normally in the given form. But for this equation, it is 2. They replace it with 2. What is y in this equation? Y would be 16, and x is 4. So we replace the b with 2, we replace the y with 16, and the x with 4. Questions on how we found x, b, and y? So we want to rewrite it in exponential form. Exponential form is b to the x is equal to y. And for this equation here, we said b was what? 2. Y is, or x is, 4. And we're saying 2 to the 4th is equal to our value of y, and y is what? 16. So this rewritten in exponential form says that 2 to the 4th is equal to 16. So the logarithmic said that log base 2 of 16 equals 4. Its exponential form is 2 to the 4th is equal to 16. Yeah, we're just switching forms. Now it's easy to check because 2 to the 4th equals 16. I can grab a calculator and say, what is 2 to the 4th power? It is 16. That is a true statement. It is a true equation. Wrong. No. We ready for B? Now we look at problem B. Again, log base b of y equals x if and only if b to the x is equal to y. That first statement's true, only if the other one is true also. Now looking at this equation, what number is taking the place of our b? 4. So b is 4. Our y value, 1. And our x value is 0. So if we want to write this in exponential form, our b to the x is equal to y. Our b value is 4. And it would be to the what? 0 power is equal to 0? Yeah. Yeah. 1 is understood, but especially writing in exponential form, we'll need to write it. 0 as an exponent, we always have to write it, no matter what. Because if an exponent is not written, it's understood to be 1. 4 to the 0 is equal to 1, and we can check that. 4 to the 0 power is indeed 1. Questions on these first two here? Let's look at the next one. We want to rewrite log base 12 of 12 equals 1. Again, I will put it back up here. Log base b of y equals x if and only if b to the x is equal to y. So when I look at c, log base 12 of 12 equals 1. B is 12. Y is 12. And x is 1. So if we wrote this as an exponential, we would have what? 12 to the first power is equal to 12. Now, normally we would not have to write the 12 to the first power. We wouldn't have to write that exponent of 1. But here, for these here, rewriting it from logarithmic to exponential, it will be nice to write it just so we know where everything is going. Questions on problem C? Are you ready for the next one? In this case here, B is what? 1/4. Y is 4. And X is -1. So if we wrote this as an exponential, what would we have? So 1/4 to the power of -1 is equal to 4. Especially when we get these fractional x or bases, it's going to be good to write parentheses around it just so we signify that that power, that -1, is being applied to the whole fraction, not just to the numerator alone. Most calculators, without the fraction, as long as we signify 1/4 to the -1, for the most part, we'll understand it's being applied to the whole thing. But sometimes it's better to just go on and put the parentheses and make sure we have it set up correctly. Because if we just apply that -1 to the top, it does not give us the same answer. Questions on C or D? How do we feel with changing it from logarithmic to exponential so far? Okay. Now, do we have to write what B, X, Y are every time? No. I did it the first 2 times so that we can see how they connect and work together. So if we look at the next one here, log base 6 of 216 is equal to 3. If we wrote this as an exponential, we would start off with what? 6 to the third, 3 is equal to 6 to the third power is 216. Log base 7 of 1 equals 0 would be 7. 7 to the 0 is equal to 1. Yes. Log base 21 of 21 equals 1 would be 21 to the first equals 21. And lastly, for this set of 4 here, log base 1/5 of 5 equals negative 1. Would be 1/5. Negative 5 to the negative 1 equals 5, yes. And this makes sense because with negative exponents, we have to move it from the top of the fraction to the bottom. So really that negative 1 is flipping it, flipping that fraction. Then we just have 5 to the first. Questions on these 4 here? Now we're going to go the other direction because log base b of y equals x if and only if b to the x is equal to y. Well, we can also say b to the x equals y if and only if log base b of y is equal to x. We can go the other direction. Now, it still holds true. For a here, our b, our base would be what? Our b would be 5. Because it's our number, we're putting it to a power. X, in this case, would be 2. And y would be 25. So if we rewrote this as a logarithm, we'd have log base what? 5 of 25 equals 2. So really what a log is saying is, as we see here, the base to what power is what's inside. So really here we're looking at 5 to what power is 25. So that's really all it's saying. And what we're looking at this here is saying, okay, 5 to what power is 25? Well, that is 2. 5 to the second power is 2. Questions on A? Now, one thing I do want to point out, when we are writing this, we do need to be careful. We do need to make sure that that 5 is dropped lower, is in that subnote. I think subnote. Because if we write it like this here, this is not log base 5 of 25. We're now saying log of 5 times 25. If we write it up there, even with that parentheses, even with that number, they're actually being multiplied together. And if the base of a logarithm is not written, it's understood to be 10. So really what we're looking at now is log base 10 of 5 times 25. So we do need to make sure that that 5 is dropped down. It is the base, it's not being multiplied. Yes? Welcome. Let's look at problem number B. Now, if we do our b, x, and y, for problem B, the value of b is 10. X would be -1, and y would be 0.1. So this here would be log base what? 10 of 0.1 equals -1. Common logs, the base is understood to be 10. If the base of a logarithm is 10, we don't have to write it. But if you're not sure, go on and write it, because log base 10 is 0.1 and log of 0.1 are the exact same thing. And we will talk about that again later. If a log's base is not written, it's understood to be 10. So on the calculator where you've seen that LOG button before, that one has the base set as 10. So log of 0.1 is indeed -1. If the base is something other than 10, we're going to have to do something called change of base. We will learn about that later, or use a different method for typing it in. Questions on these so far? We ready for the next one? Eight to the 2/3 is equal to 4. Yeah, kind of got ahead of it. So B is 8, X is 2/3, Y is 4. So this here would be log base 8 of 4 equals How about the next one? 6 to the -3rd equals 1 over 2/16. So I'm not going to specifically denote AB or BXY, but we'd have log base what? 6 of 1 over 2/16 -3. Questions on this here? Questions on these two here? All right. 9 squared equals 81. So log base, what? 9 of 81 is equal to 2. Because we're saying, because really log base 9 of 81 is saying 9 to what power is 81. How many times do we need to multiply 9 by itself to get to 81? And that is twice. 20 to the -1 equals 0.05. This would be log base what? Base 20 of 0.05 equals -1. So here we're saying 20 to what power is 0.05. Well, that seems kind of weird. We would say -1, yes? Well, 0.05 as a fraction is 1/20th, 1 over 20. So 20 to the -1st power, we'd have to move it from the top of the fraction to the bottom, so it is 1/20th. That's all it's saying. We put it to the -1st power, which took it from the numerator to the denominator. So sometimes it's easier to see some of those if they give it to us as a decimal, as a fraction. 16 to the 3/4 is equal to 8. This here would be what? Log base 16 of what? 8 equals 3/4. Log base 16 of 8 is equal to 3/4. And lastly, 15 to the negative 2 is equal to 1 over 225. So we'd have log base what? 15 of 1 over 225 equals, as we're saying, 15 to what power is 1 over 225. Now, two things that are very helpful. Log base b of 1 is equal to 0. Because if we took that logarithm and rewrote it in exponential form, we would be saying b to the 0 power is equal to 1. And this is true as long as b is not 0. We cannot take 0 to the 0 power. It does not work. It does not equal 1. Especially in algebra and a lot of other cases. There's a few specific areas where 0 to the 0 power does work. We do talk about it. We do use it. But very specific cases. Also, another one that's useful, b, log base b of b. When the base and what's inside the logarithm are the same, b equals 1. Because if we rewrote it as an exponential, it'd be b to the first is equal to b. b to the x is equal to b. And we can use that, and kind of as we've been talking with these logarithms, to figure them out, to solve them. Log base 4 of 64, we're wanting to know what this equals. Log base 4 of 64. Well, this is the same as saying what? 4 to the x is 64. So we're trying to figure out how many times we need to multiply 4 by itself to get to 64. So we can try squaring it. So we can say 4 squared is 16. We can try a bigger power. We can try 3. Really, we can say that 4 to the third power is indeed 64. So x has to be what? 3. Or the other way we can do this is we can rewrite 64 as 4 to the third, because I just trial and error found that 4 times itself 3 times is 64. So I can replace that 64 with 4 to the third. Now we will get to it. We will come across this later on in the notes or later in a different note sheet. This is the one-to-one property. 4 to the x is equal to 4 to the third. The only way that we can have the same bases on both sides and them be equal is if the exponents are equal also. So in this case here, the bases are both 4. We can get them to be the same. It means that their exponents have to be equal to. Because the only way I can multiply 4 by itself a certain number of times and it'd be equal to 4 to the third power is if their exponents are the same. So x has to be 3. Questions on this here? Now let's look at b. Log base 5 of 0.2 equals x. In exponential form, we're saying 5 to what power is equal to 0.2. Questions on how we change it from logarithmic to exponential? Interestingly enough, if I actually rewrite 0.2 as a fraction, it is 1/5. This is a little bit nicer because really what we're saying here now is 5 to the x is equal to 1/5. Questions on this here? Now, at this point, we can't use the one-to-one property because the bases are not both the same. One of them's 5, the other is 1/5. But we can actually rewrite this 1/5 in a different way. Because I can move a number from the bottom to the fraction to the top, or top to the bottom, but doing so changes that exponent, its exponent, from positive to negative, or negative to positive. So it is possible to move this 5 to the top, really saying we have 1 times 5, but its exponent has to go from positive to negative. What is the exponent attached to 5? 1. So really what we're saying is that we have 5 to the x is equal to 5 to the negative first power. Are the bases the same? Now they're both 5. And according to the one-to-one property, it means that the exponents have to be also. So the only way I can multiply 5 by itself and get 1/5 or 0.2 is if I multiply it by itself -1 times. We feel comfortable saying that. Did you ever think, especially starting negative numbers or exponents, you'd be able to say, yes, I get 5 to the -1 power, makes sense that it's 1/5? Yes, I understand, or kind of I've got an idea of what multiplying something by itself a -1 time is. But that's all it is we're just saying we're moving it from the top of the fraction to the bottom. Questions on either one of these here? And as we look at the next one, log base 1/5 of 125 is what? We want to figure that out. We need to see what we need to multiply 1/5 by to get to 125. Is 5. Can I multiply 5 by itself a certain number of times to get 125? Well, yes, because at this point we haven't figured out or come across any way we can do it otherwise. Well, I can grab a calculator and give it a try. 5 to what power? What do you want to guess? 5 to the -3 is 1 over 125. Well, what is 5 to the third? Figure that out. 5 to the third is 125, yes? But we're not looking at 5, we're looking at what? 1/5. We actually saw that 5 to the -3 took it from 125 to 1 over 125, yes? So interestingly enough, if I tried it with, say, 1/5 to the -3, it would be, because that negative is taking that 1/5 and flipping it to 5. We multiply it to the, or put it to the third power, we do get 125. We can look at the one-to-one property with it also. Because really we're saying 1/5 to what power is 125. That's the exponential statement. Now, luckily enough, by the time we get to the end of the chapter, especially a problem like how we have it written, log base 1/5 of 125 equals what, is going to be a nice problem, should be, because we will go over by that point how the calculator can do that for us. But at this point here, I need the bases to be the same. And as we saw, 125, we don't really need the parentheses, is indeed 5 to the third power. On the left-hand side, 1/5, I can bring that 5 from the bottom of the fraction to the top, so it is the same as 5 to the negative 1. Powers of powers multiply, so negative 1 times x is going to be negative x. So we're really saying 5 to the negative x is equal to 30. If the bases are the same, the exponents have to be the same as well. So we're saying negative x equals 3. Or really, x is equal to negative 3. Questions on this here? We'll look at this last one here, log base 36 of 6. So this is kind of the funny one, because we're saying 36 to what power is 6? We're saying 36 to what power is 6? It should be something less than 1, yes? And it's probably not going to be negative, because if we got negative 1, it's just going to be 1 over 36. Now, I know 36 is 6 to what power? It can be 6. Because 6 times 6 is 36, yes? So 2. Or really, what we can say is that 6 to the 2x is equal to 6. Are we comfortable saying this? Yeah. Because 6 squared is 36. Powers of powers multiply. Now, it seems odd. Why are we going this route? Why is this where I want to be? What is the exponent attached to that 6? 1, yes? So 6 to the 2x is equal to 6 to the first. Are the bases the same? Are both bases, we have 1 and they're both 6, yes? If the bases are the same, the exponents have to be the same as well. Which means for us that 2x has to equal 1. How would we solve this here? Divide both sides by 2, telling us x is 1/2. 36 to the 1/2 power is indeed 6. Now, for the most part, ABC, we can logic our way there. We could get there eventually. D is not, we can get there. It just takes a little more work to get there. And interestingly enough, the graphing calculator, we know, has a lot of nice things. If I hit math and scroll down, not where I wanted to go. One of the options that it has is log base. And if I hit enter, it will actually say, what is the base? Well, I'm going to tell it is 36. And what's inside the log is 6. Tells me it's 0.5. Now, unfortunately, if I go log of 6, it's going to tell me it's this. Because the base for this log is understood to be 10, not 36. Questions on any of this so far? Now comes the whole question is why is any of this important? Because for the most part, as we see here, these are all nice. Yes, we can get there. We can manipulate the numbers. Because even if I said 2 to the x is equal to 4, we know x has to be what? 2, yes? Because 2 squared is 4. Okay? 2 to what power is 5? We don't know. So this here as a logarithm would be log base 2 of 5 is equal to x. 2 to the 2.321928095 continuing on is this here. It's an irrational number. This is why logarithms are nice when we don't have this nice power that we can find. But we'll finish this tomorrow.